Hello, hello. Good. So, oh, it did. Okay, okay.
Yeah, this shouldn't have feedback because they're intentionally not face first.
Should this pop up or let me know because this is still in presentation mode. Huh? It's up? Oh, okay. Good. Or no. No, there we go. I'll just wait like another minute. People are still streaming in and then I'll get started. So,
You can just play around with this. You can just get started. No, we can't. Give us another 5 minutes. Let's start at 9:05.
okay. I don't want to take too much time away from the time.
Sure.
I don't know how
If my part is going perfect, it's okay. This is mostly for the I'll take about 5 minutes.
Dude, I don't have what? Why?
Hello. Okay, hi everyone. We're going to get started now. Welcome. Welcome everybody. I'm Manu Sridharan. I couldn't be happier to welcome you to SPLASH 2024 and OOPSLA 2024. I'm just going to have a few introductory remarks and then we'll move on to our first keynote. So, thus far, things have been going great, and we have quite a large splash this year. So this is numbers as of yesterday. We had 616 registered attendees, and 46% are students, which is fantastic. Welcome to all the students here. And people traveled from all over, 56% North America, but also 28% from Europe, 13% from Asia. So for those of you who had long journeys to get here, I hope it was smooth and a warm welcome. So just to give you an idea of all the things that are happening at Splash this week and have happened, we had 5 conferences, or are having. OOPSLA and Onward are the next 3 days, and SLE, GPCE, and SAS have already completed. Today we have Rebase, which is a track of invited industry talks, and tomorrow we have our education track, Splash-E. We have several student-focused events. So PLMW, the mentoring workshop, and the doctoral symposium have completed, and starting today at the reception, we're going to have the student research competition. And finally, we had 10 fantastic workshops that just wrapped up yesterday. So I want to acknowledge our sponsors. We couldn't make Splash happen without them, so we have several generous sponsors this year, and I encourage you to check out any materials they have available, or if you go to the website, you can click through and learn more about them. I owe a huge thanks to the organizing committee for Splash. So I did a very small amount of the work to organize this. These folks on this slide and this slide, it's such a huge committee, I can't go through every name, but all I can say is they were amazing. They were completely on top of things. They made my job very easy. So anyone here who's on the organizing committee, could you please stand up and could we give them a round of applause, please? So thanks for that. And I have to call out the amazing efforts of our student volunteer team and our video team. They've been doing an amazing job of running the conference, handling streaming, handling AV issues. I've just been astounded by how good of a job they do. So any student volunteers here, could you please stand up and could we give them a round of applause? Thank you so much. So we do have a code of conduct. You all should have read it as part of the registration process. I just wanted to emphasize that there's no tolerance for unwelcome, hostile, or disruptive behavior or speech that intimidates, creates discomfort, or interferes with a person's participation or opportunity for participation at the conference and all associated events. So we take this very seriously. I'd also like to let you know that there's an organization at the SIGPLAN level called SIGPLAN Cares, and they're available to support any community members who've experienced harassment, discrimination, or bullying, and to help you with information on how to report any unacceptable behavior. So these are the folks who are on the SIGPLAN Cares Committee. Unfortunately, I don't think any of them are here in person, but if you need to talk to someone in person about any such issue like this, please come talk to me. I wanted to briefly mention our social and networking events that are going on. So Michael Koblenz, the DEI chair, are you here? There's Michael. So everyone take a look so you know Michael's face. Michael's been our fantastic DEI chair. We have a bunch of events organized. So there's going to be a newcomers coffee. That's at the first coffee break today. And if you find Michael, he'll give you an idea of where people are meeting. There's a job market lunch today that's going to be joint with the main lunch. We'll have some tables kind of marked off for that. There's the SIGPLAN mentoring lunch today. These are for those who are part of the SIGPLAN M program that's going to be in Pacific Sea. Tonight we have a reception and a poster session and also the student research competition. There's a women's dinner tonight. You can see the location on the schedule on the website. And tomorrow, we'll have our LGBTQ lunch, and on Friday, we have our underrepresented minorities lunch. And for those two events in particular, I wanted to mention that please feel free to attend if you'd like to join those events, even if you didn't sign up during the registration process. Okay, and then the last thing I just wanted to say is enjoy Pasadena. Enjoy the conference for sure, but please feel free to take a walk in walking distance. There's good coffee shops, restaurants, shops, interesting architecture, and we have a web page up that lists a few other attractions that you might be interested in checking out while you're here. So thanks so much, and now I will turn it over to Alex Batanin, who will be introducing our first keynote speaker.
Hello, I'm Alex. I'm the PC chair for OOPSLA, together with Ivan. Today it is my pleasure to present you a local celebrity. He's a member of the Principles of Jazz band that last performed 13 years ago at an esteemed SIGPLAN venue. Todd was also a student of Craig Chambers at University of Washington, who supervised a small group of very distinguished people, such as Todd Milstein, who chose an academic path and is now a department chair at UCLA. But others included Jeff Dean, I think he's a chief scientist at Google, and others, but we have Todd. Todd worked on multi-methods in Cecil programming language originally, which is a big thing for me because I was always a big fan of Dylan programming language, if anyone knows that. He was also the first PC chair of OOPSLA who invited Manu and myself to serve on the OOPSLA PC 10 years ago. Maybe there is a conflict of interest here, but unfortunately this time he refused my invitation to serve on the OOPSLA PC, but I guess being a department chair has its perks, that's right. More recently, Todd worked on network verification tools to analyze network, including well-known Bedfish configuration analyzer, an excellent example of sort of research impact on industry because it's used in Amazon, Oracle, and many others. Recently, he worked on the BGP configuration verification, and if you don't know what that is, in October 21, the whole of internet went down because Facebook stuffed up their BGP configuration, so like just to explain the kind of impact that can have. So without any further ado, and since Manu refused my persistent request last night to provide a guitar, instead we'll have Todd present a talk on how everything is a program. Thank you.
Okay, great. Thanks, Alex. I really appreciate it. And you know, OOPSLA was really my first academic home. It's where I published most of my PhD dissertation work many years ago. I've been coming here for 25 years, so it's really an honor to be speaking. So what I want to tell you about is kind of related to what Alex was talking about, my experience in how the perspective of this community, the PL perspective, can really help solve problems and have a big impact in other communities outside of PL. And this is based on the work I've been doing for the past several years in applying PL ideas to computer networks, but I think the ideas that I'm going to present are more general than that. So I'm going to be talking about these two internet protocols that underlie everything we do online. There's DNS, which is the domain name system, and there's BGP, which is the border gateway protocol. And at a high level, what they each do is pretty simple. So what DNS does, like if you want to watch Netflix, are we okay? Is it okay? Yeah. Higher? Okay, great. Now I feel like I'm hosting a talk show or something, but okay. So if you want to watch Netflix, hopefully you'll wait till after the talk. But if you do want to watch Netflix, two things at least have to happen. One is that DNS has to translate the domain name netflix.com into an IP address. That's how we actually communicate on the internet. And so that's the job of DNS. And then what BGP does is, once you know the IP address, you need a route to reach there from your destination, from where you are to the destination, in this case Netflix. So like from here, you'd have to go through the hotel's Wi-Fi, and then to their physical network, and then from there to their ISP, their internet service provider, and so on, and eventually get to Netflix. And so you can see that these two protocols are fundamental to everything we do online. We always need to be translating domain names. We always need to be computing routes to destinations, and for that reason, these are also what underlie essentially all the outages and security vulnerabilities that happen at the network level on the internet. And so much so that there are a bunch of kind of like memes that go around in the network engineering community about this. So one is that it's always BGP. Like no matter what else you think the problem is, if there's a problem, it's BGP's fault. Of course, then people say the same thing about DNS. Here's a haiku that someone wrote about DNS. Like, it's not DNS. There's no way it's DNS. It was DNS, you know. And, you know, you can split the difference too. This one is about an internet outage in India, and it says at the bottom it's always BGP when it's not DNS. So, you know, why are these things so fragile? Well, I think there are two reasons. One is that the protocols themselves are pretty complex. So they're defined in these things called RFCs, requests for comment, which are these English documents. And although at a high level what the protocols are supposed to do is simple, over time they accrue sometimes dozens of these documents to extend them for expressiveness reasons, for performance reasons, and so on. And so just implementing a high performance, you know, version of this protocol that conforms to all these documents is itself really challenging. And then the other aspect is that both of these protocols are configured. So like BGP doesn't know which routes to the internet I want to use and which ones I don't want to use, which I might have preferences there for security reasons or for financial reasons or whatever. So the way these protocols work is every organization that runs DNS and every organization that runs BGP, which is every organization on the internet, has to configure it. And you actually have to configure it device by device. So if you have 20 devices in your network, each device has to have its own configuration. And there are these low-level files. I'm showing examples of DNS and BGP file configurations here, but the details don't matter. But the point is that these low-level configurations, which are sometimes thousands or tens of thousands of lines, together determine my policy, which routes to the internet I want to allow, which ones I don't want to allow, how to answer DNS queries, and so on. And so you can imagine that it's easy to get these things wrong. And so we got these two problems, low-level configurations and complex protocols. And what I found is that kind of time and again, the perspective of our community can really provide a lot of value in solving these problems and have a big impact on kind of correcting these problems in the real world. And so I'm going to kind of boil it down to three slogans that I'll then try to illustrate through some of my work. So the first one is that everything's a program. And what I mean by that is that programming languages are amazing tools for modeling complex systems. And so we can model something as a program even if it's not really a program, even if it's in hardware, or even if it's really a globally distributed internet protocol, or even if it's a configuration file. We can think of it as a program. We can model it or model salient aspects of it as a program. And once we do that, we can then bring to bear the techniques we know how to do, so we can give it a precise semantics. And that's where my next point comes in, which is that being pedantic is a virtue. So I think this community is really pedantic. Or speaking for myself, I'm very pedantic. Like if you show me a new programming language, I'll probably first ask, well, what happens if this happens and this happens and this thing happens and there's this weird corner case there? And I think we're often told that like 80-20 rule, like just focus on the 80%. But I think actually what I've found in practice is that being pedantic really matters, because once you've specified completely, the semantics, including all the corner cases, then you can actually make guarantees, meaning you can comprehensively reason about that semantics. And again, I think this is something we're often told, like, well, soundness proofs, like we just do those because this is the weird community that thinks those are fun to do, and you need it to publish a paper. But actually what I've found is really just the opposite, that these guarantees really matter in practice, and I'm going to try to demonstrate that. Okay, so I'm going to focus on 2 examples from my work in the rest of the talk. The first one is about low-level configurations. That's about BGP, and I'm going to tell you about how to catch network reachability errors before they exist in the live network. And the second one is about some work we've been doing on DNS, and I'm going to tell you about checking DNS implementations and finding critical bugs in DNS implementations. Okay. So let me first tell you what the problem is that we want to solve in this first part of the talk. The problem is pretty straightforward. It's about verifying network reachability. So if I have this little network, A, B, and C, I might want to make sure that a certain class of traffic can always reach from A to C, because that's how we communicate on the internet. If that class of traffic can't be delivered, then that's how we get network outages. But at the same time, I may also want to ensure that a certain class of traffic can never reach from A to C for security reasons. It should be dropped if that traffic is attempted. The way things work is in network forwarding is that every node has what's called a forwarding table. So for example, this is a simple forwarding table for B. It says that if B and it tells it what to do when it receives a packet. So what it says is if B receives a packet that's destined for 10.2.anything, it should send it to A. And if B receives a packet that's destined for 10.3.anything, it should send it to C. But if it receives this more specific kind of packet for 10.3.12. something, then it should drop it for security reasons. And so every node in the network has one of these forwarding tables, and together they determine what's going to happen when a packet enters the network. And so around 2011, 2012, I started to see, and my colleagues and I started reading these cool papers coming from the networking community where they were trying to tackle this problem of verifying network reachability. This was one of them. It was from UIUC. There was another one called Header Space from Stanford. And their idea was the following, that these forwarding table rules, we can code them up as logical constraints. We can model them as logical constraints, and therefore then we can use something like a SAT solver or some other kind of constraint solver to check reachability problems. Check reachability properties. And that was really cool to see because, of course, this is something that we in our community do quite a lot as well to reason about programs. But one thing we were thinking about when I was reading about these papers with my colleagues, especially this one actually says it in the title, they were calling this static checking for networks. And of course, as a PL person, I'm like, how dare they use the term static checking? That's what we do. Do they really even know what static checking is? And we can ask, is this really static checking? And the thing to understand is that these forwarding tables actually live as part of the runtime state of the network. And so for those papers, for those projects to do what they need to do, what they do is they have to log into each network device, grab its forwarding table. Now they have the collection of forwarding tables. Now they can run their analysis. And so what that means is that any bug that they catch, if they find, let's say, a security vulnerability, then that bug is already living in the network. It may have already been impacting traffic in the network. And so, when we were reading these papers, we just asked this simple question, which is, okay, well, they're finding bugs, but they're already living in the network. Is it possible to identify these kinds of network reachability errors ahead of time, before they exist in the live network? Which is, of course, a very kind of PL-type question to ask. And this simple question has really animated the collaborative work that I've done over the past dozen years in this direction. And it's really still an unsolved problem. I mean, we've made a lot of progress, and that's what I'm going to tell you about. But the problem in its full generality is really a challenging programming languages and networking problem that we're still working on today. But the progress we've had has really made a lot of impact in terms of how people operate real networks today. So let me make this stuff precise before I go into some details of how our work handles this problem. So this is like a programming languages person's view of networking. This is like what I know about networking. So, you know, you have these forwarding tables, and I showed them before, like these rules that tell you what to do when a packet comes in. And so we can model them from a PL point of view as a function that, given a packet, gives you back a path through the network that that packet takes, right? So like if you inject a packet at A, maybe it'll go all the way to C and get delivered, or maybe it'll get dropped on the floor. And the forwarding tables determine what's going to happen there. And so these prior papers that I was reading about in 2011, 2012, what they were doing was, given a set of forwarding tables, I'll call it T, they want to verify some reachability properties. So they were verifying things of the form like this. So if phi is a property that I care about, some reachability property, they were verifying properties of the form for all packets P, phi holds on the trace of that packet through the network. And so actually, you know, there is a sense in which they were really doing static checking. So because there's a universal quantifier there, so that means they're doing static checking. Because, you know, they're not really just checking the packets that happen to be traversing through my network. They're actually checking all packets. But again, the problem is that any bug that they find may have already impacted the network, because those forwarding tables are living in the network. And so that's where BGP comes in, which I mentioned at the very beginning of the talk. BGP is a routing protocol, and so it's the thing that actually produces these forwarding tables. The way it works is that nodes advertise to each other. Like node A might tell node B, hey, I know how to reach Google. And then node B will look at its configuration and decide, oh, okay, should I keep that and keep track of that, and now I know how to reach Google? Or should I drop it because I prefer a different route to Google, or whatever? And so you can think of BGP, if I were to model it as a program, as a function that takes the set of configurations of the network and produces the forwarding tables. And so BGP is a higher order function, or it's a meta program if you want, because it's producing another program, which is these forwarding tables. I also have this other argument there, the environment, because it turns out that BGP doesn't just run once. It's running continually as the network dynamics are changing. So for example, like if a link fails in my network, then BGP has to rerun to route around it and find new routes to destinations that you care about that don't go through that link. And so in general, you can think of BGP as a function that, given a set of configurations and given an environment, a set of links that are up and down, things like that, it determines the forwarding tables that the network's going to use. So now we can start to think about what it would mean to do kind of static checking for the network. If I want to verify something offline, I just want to verify network reachability properties given just the configuration C of a network, without having to touch or access the live network. Now I need to solve problems like this. So I want to prove that, you know, let's say I'm given a particular environment E, I can run BGP with that configuration in that environment, get a set of forwarding tables. I can run a packet through those forwarding tables and see how it behaves and see if it satisfies property phi. But now I want to do that for all possible packets, and I want to do that for all possible environments that BGP could live in, that the network could live in. So you can see that this is actually way more complicated, way more difficult than the original verification problem. It's more difficult for two reasons. One is that now you have to reason about BGP, which is a distributed routing protocol, which is really complex. You have to reason about these configurations, which are really complex. And you want to do this for all possible environments, not just for all possible packets. And so, but if you can do it, then you've done something really cool, which is you can now verify reachability properties of the network without actually accessing the network at all just given the configuration files. And so, as I mentioned, we're still working on this problem. We've made a lot of progress, but this is still kind of, we'd like a general solution to this problem, and this is really still a challenge for the network verification community. But back in 2012, when we kind of this was the shift in our mind. We sort of saw the papers doing the thing on the top, and we said, okay, we want to do the thing on the bottom, and how would we do that? And so we started this project called Batfish, whose goal was to at least in part, address this problem. So I'll give you a quick timeline on Batfish, and then I'll go into some of the details about it. So we started in 2012. We wrote the first paper about it in 2015, and so it was a joint research project with my group at UCLA and my colleagues at Microsoft Research and USC. Three of us, Ari and Ratul and I, we started a company in 2016 to kind of increase the impact of Batfish. and worked on that for a while. In 2022, the team moved to AWS from the company. And at this point, Batfish has had quite a lot of impact. It's an open source project. It's been open source from the beginning, but now it's managed by AWS. It's used in many companies and organizations in production to verify security and reliability properties of their networks, including the largest tech companies, some of the largest tech companies. Oracle built a tool for their virtual cloud customers to check properties of their virtual networks, and that's also using Batfish. And many other researchers are building on Batfish for their research as well. And so what does Batfish do? Well, Batfish gives up on the full problem that I'm trying to solve. It says, okay, remember, we want to prove things for all possible environments, but we're going to give that up for now. We're going to say, okay, suppose that you give me your configuration files, and you give me a particular environment that you care about, like maybe the environment where all the links in my network are up, or maybe the environment where one particular link is down, and I want to see what's going to happen in that case. So Batfish parses it into a data model. Now it's got the two inputs that we need for BGP, so it's going to simulate what BGP would do given those configurations and that environment in order to yield a representation of the forwarding tables that would exist in the real network. And then we can ask questions like fee our verification queries and either prove that something holds, a verification query is satisfied, or give back some kind of bug report. And so the result of doing this is that now we have a capability for networks that we're used to from software but really didn't exist before, which is we can verify configuration changes before they're deployed. So if a network engineer makes a change to a configuration, which happens all the time, they can now run Batfish, ensure that the reachability properties they care about for their networks are being satisfied, and only then push it to the live network. And of course, you would never push code directly to production without testing it first, but this wasn't the way that networks were operated before this. And so if you look at this, you may say, like, what's the big deal? This looks like obvious. You're just building a simulator for BGP. And in a way, that is what it is. But I think it wasn't obvious and it wasn't easy for two reasons. One non-technical and one technical. The non-technical reason is that, like I said, this is really far removed from how networks are operated in practice or were operated in practice. So basically, all network reachability checking was done live in the network. Like you would push a change and then you would send around some test packets and see that everything looked okay, and you would monitor over time and to find errors. But the idea that you would actually check like deep reachability properties offline just wasn't even in the air. It wasn't something that network operations people were even thinking about or didn't even know that they wanted. But the other thing is that even if you decide to do this, actually that little arrow that says simulate BGP is like a 12-year project to get that right, because for two reasons. One is like we have to get it exactly right, because if the forwarding tables we produce are not the forwarding tables that will be in the real network, then we're just verifying the wrong thing. And so we've got to understand all the corner cases. BGP is really complicated. It's actually even more complicated than I'm showing because there's multiple different configuration languages. There's multiple routing protocols, not just BGP, and they interact with each other. So you've got to get all that right. And also, if you just do that simulation in a naive way, like message by message, it's not going to scale to realistic size networks. And so I think that's why the PL perspective is really critical, because for us, static checking is a natural idea. Like, let's do something offline. Let's get a guarantee before we run our program. And that's something that kind of hadn't occurred in the networking world, really. In limited ways it had, but not to the level of being able to check reachability properties. And then, as I said before, we're willing to get our hands dirty and be pedantic, understand all the corner cases of BGP, and really get that arrow right so that we're making sure that we're getting the right forwarding tables. And the other aspect that's important is that for performance, like I said, you can't just do a message-by-message simulation. This is where modeling and abstraction come into play, which is something that our community is also very good at. So, like, in this setting, we don't care about all the intermediate states of BGP. We don't care about the transient states along the way. We just care about the final forwarding tables. So we can do things much more efficiently than just message by message, as long as we make sure that we get the same forwarding tables out at the end. So we can make a lot of optimizations if we understand the semantics and can kind of do things at a higher level of abstraction. The other part of this I want to say is that our goal was to produce these forwarding tables in order to check reachability properties, and that is a big way that Batfish is used today. But one other big benefit was almost equally important, was something we didn't really think much of at the time, was just that we treated these configurations as programs in the sense that we treated the configuration languages as full-fledged programming languages. We built this essentially compiler infrastructure that parses to a data model, which we would call an IR, an intermediate representation. And that hadn't been done before, at least not for full configurations. And that's because like configurations aren't really programs. They're like this weird grab bag of like random stuff. Like, you know, you say like what version of the configuration language you're using and what host you're configuring and some simple parameter settings, and you declare interfaces, which are your connections to other devices in the network, and you declare access control lists that say which traffic you want to permit and deny for security reasons, and you say which routing protocols you're running, and you give all kinds of parameters for them, and you configure these routing protocols. So there's really like a grab bag of things going on here, but the thing is that by treating that all as a unified language and parsing it into a common intermediate representation, we essentially get something like an LLVM for network configurations, because now we have a structured representation of the configs, and we have an API to access it. And so now it's very simple to do things that were complicated before. Like if you just want to enforce a naming convention on your configurations, or check that a particular parameter always has a particular value in your network. These little stupid things were actually causing real problems in real networks before. And now you can write like a 3-line Python program and check this and make sure that these things are satisfied before you push your configuration changes to the network. And not just simple things too, more complex things too. Like one example of that is, I mentioned there are these access control lists. And so they're like sequence of permits and denies that say what traffic I want to allow, what traffic I want to drop. And so one of the things we've built on top of our data model are tools for like full functional correctness reasoning about these access control lists for all possible packets. So one example is we have a tool that can compare two access control lists and tell you exactly their behavioral differences. And many companies have used this. For example, eBay wrote a blog about using this a few years ago where they refactored one of their access control lists to be 80% smaller, and they were able to use this tool to verify that for all possible packets, the new version was equivalent to the old version. So the point I want to make there is that that has nothing to do with BGP. It has nothing to do with routing. It has nothing to do with the forwarding, producing the forwarding tables. But just the fact that we had a structured data model, which is something we do all the time in our community, was able to have a big impact there. And so the summary of this part of the talk is that, you know, we sort of take these points for granted in our community, but these are really powerful tools that can have a big impact on other fields. I want to end this part of the talk by trying to resolve this limitation. So I mentioned that, you know, we really want to prove things for all possible environments. We don't want to just reason about one environment at a time. That's not going to scale. We've been doing some work in the last few years that gets around this limitation, and it takes this idea of configurations as programs kind of even further. So I'm going to give you just a taste of that. So here's an example. Suppose this is my network, and my network is connected to a private data center that is only for me, and to some internet service provider, which is how I'm reaching the internet. And so a natural property that you would want to ensure is that the ISP shouldn't be able to communicate with the data center. The ISP can't query the data center, get access to the data, or update the data, things like that. And so your BGP configurations need to ensure that. The BGP configurations should ensure that essentially, remember how BGP works, different devices are advertising routes to each other, like, hey, I know how to reach Google, I know how to reach whatever. So the BGP configuration should make sure that the data center routes are never being advertised to the ISP, so the ISP never learns how to reach the data center. You could ask this question in Batfish, and Batfish would just do like a global simulation and then answer the question. But you'd have to do that one environment at a time, environment after environment. Try the environment where no links are failed. Try the environment where this particular link has failed, and so on. And that's not going to scale. But what we can recognize is just like programs, configurations have a lot of local structure to them. They're made by human beings, and so you know, they're not designed randomly. And if we understand some of that local structure, we can actually do a much better job. And so, like, so the point is, how is the BGP configuration of this network going to ensure that data center routes aren't sent to the ISP? Well, here's a standard way that a configuration might do that. There's this node, N1, that's connected to the data center, is going to paint all the routes that are advertised by the data center. It's going to paint them orange. Now, it's not actually going to paint them orange, but it's going to tag them in a particular way. And then this node over here, N2, its BGP configuration is just going to make sure that it never sends orange routes to the ISP. And there's one other important property, which is that none of the other nodes in the network are going to repaint an orange route. If something's orange, it stays orange. And so what you can see is what that means is the network configurations are actually setting up an inductive invariant of my network, or the combination of the configurations and the way BGP works is setting up an inductive invariant that data center routes are orange. That's established at N1 and that's maintained by all the nodes that don't repaint these routes, and then it's used at N2. And so what that means is that to check this property that I care about, really all I have to check is that each little node is doing its little job. N1 is doing its job in painting everything orange, and N2 is doing its job in dropping all the orange routes, and no one else is repainting orange routes. And if I check all those simple things, I've ensured this property, but more to the point, if you think about it, that logic doesn't have anything to do with what nodes failed and what links have failed and which haven't. It actually holds regardless of link failures. Like N2 is dropping all orange routes. It doesn't care what links have failed in the network. It doesn't care which of its neighbors it's connected to. And so actually, if we can check these local properties, we're not only guaranteeing it for one environment, we're actually guaranteeing it for all possible environments that the network could live in. And of course, this is the way we verify programs too. That's the point I'm trying to make, is that you can apply some of those ideas, but you have to adapt it to this setting. Even though this is a distributed routing protocol, we can treat it logically as a centralized program that has an inductive invariant, and you can actually make that precise. And so we've built a tool based on this idea called Lightyear. So it requires more than what Batfish requires. You have to give not just the property, the end-to-end property you care about, but you have to give these local invariants that hold. But if you can do that, or that you think hold, then if you can give that, then what we do is we check that these local invariants actually hold, and we check that they imply the global property, and then we can give a stronger guarantee, a much stronger guarantee than what Batfish can give. And this is actually being used right now in the wide area network of a major cloud provider. And one cool thing about it is because it's local, it's essentially a modular reasoning tool for BGP, it's much more scalable. So no other tool has scaled to the size of a wide area network with tens of thousands of devices. And it can scale and also actually give you stronger guarantees than what you can get with like a simulation. Okay, so everything's a program. Yeah, forwarding tables are programs, BGP is a program, network configurations are programs. We can be really pedantic, and then we can precisely model BGP and its configs. And once we do that, we get this capability that we've never had before, which is the ability to make proactive network tools. Tools that can give you guarantees about your network in advance. And because we were pedantic, these tools can be trusted. Okay, that's the end of that part. So now I'm going to switch gears. I'm going to talk about a different protocol and a different problem. So the problem we're talking about now is we have implementations of protocols. That was about configurations. Now we're going to talk about the implementations. The implementations of the protocols are complex. They're buggy. How do we get them right? And I'm going to talk about that in the context of DNS. And I'm going to tell you how we went from having a formal semantics for DNS to finding a critical denial of service attack in DNS. So first, let me tell you what DNS is. Suppose you want to reach the UCLA homepage. What's going to happen is, well, that's a query. It's going to go to this thing called a DNS resolver. Its job, as you might guess, is to resolve the query and produce an IP address. And the way it's going to do that is it's going to interact with these things called DNS name servers. The thing you have to understand first is DNS is tree structured. It's hierarchical. You've got a root. The domain names are hierarchical, right? You've got a root, and then underneath the root, you've got the top-level domains like com and edu and gov. And then underneath edu, for example, you've got ucla.edu. And so it's tree structured. You've got name servers at every level of the tree. Each name server has what's called a zone file, which is its configuration, which tells it what to do when it receives a query. That's the thing that knows, oh, here's the IP address for this place, or here's what you should do if you get this query, because DNS doesn't know that by itself. And so what's going to happen is you're going to start at the root name servers, and you're going to ask this query. You're going to pick one of the root name servers, ask this query. And in this case, what's going to happen when it looks at its zone file, the root name server for the whole world doesn't know the ucla.edu homepage IP address. But what it's going to say is, well, I don't know that, but I do know the address of the name server that's one level down from me, which is the edu name server. So go ask the edu name server. And then the resolver is going to go ask the edu name server, and the same thing is going to happen. It's going to come back and say, well, I don't know the IP address of the UCLA homepage, but I do know the address of the ucla.edu name server. So go down and go ask the ucla.edu name server. And finally, when we ask one of the name servers for ucla.edu, it's going to say, okay, yeah, here's the IP address. Now we've got the IP address, and we can go view that web page. So that's happening when you view web pages. it seems at a high level kind of simple, but it's pretty complex. It's complex for two reasons. One is there's non-determinism. I kind of showed that. There's multiple name servers at every level of the hierarchy, and they can be configured differently, and so based on which one you go to, you can have different behavior. And this is actually something that is a common problem. The other thing is that the way a name server behaves is dependent on this thing called a zone file, which is its configuration. It's a sequence of records that say, if the query looks like this, then you should do this. If the query looks like this, then you should do this. And I kind of gave a flavor of it. Like it might say, go to this name server, or it might say, here's the IP address you're looking for. But there are actually lots of other things it can do too. Like it can do aliasing. Like it can say, oh, you asked me for foo.com, but I'm going to treat that as if you asked me for bar.com. And it can actually just rewrite your query in interesting ways and say, you asked for this query, I'm going to completely rewrite it to this other query that I'm going to answer instead. And there may not be exact matches for the query you asked, and so there's wildcard matching, so it may be inexact matching. And so these things are complicated. Right, and so if we want to make the DNS system robust, we kind of have to tackle three different problems. There's the DNS resolvers, there's the DNS name server implementations, and there's the zone files. And all three of them can go wrong, can and do go wrong. And so this is kind of the ecosystem we've been working in, trying to make more robust and reliable for the last 5 or 6 years. I'm going to tell you about one particular project, which is about the name server implementations themselves, and how do we make sure that the name server implementations themselves are robust. So these are the implementations of the fundamental DNS protocol. There are many of these implementations out there, and they're widely used, both open source and closed source. So our goal isn't going to be to kind of create a brand new one that's fully verified, or even to try to fully verify one of these things. Our goal is to, more modest but still useful, is to do test generation. But in particular, to test for a wide variety of behaviors as specified by the RFCs, by the specification for DNS. So if we think about what a name server is, again, as a program, it's just a function of two inputs. It's a function of a query and a zone file. Given a query and given a zone file, the name server should behave in a particular way as specified by the DNS protocol. If we want to do test generation, therefore, we need to create these pairs of queries and zone files. A pair of a query and a zone file is a test that we can run on a name server and see how it behaves. There are two main challenges for doing that. One is that zone files are really highly structured. They have a lot of syntactic and semantic dependencies, like you can't have duplicate records of a certain kind, or if you have a record of this kind, you have to have a record of that kind. The other thing is that the behavior of a query depends critically on what the zone file says. So, if you want to generate interesting behaviors, you really have to jointly generate the query and the zone file. You can't separately generate them, otherwise you're unlikely to get deep into some interesting behavior that DNS can do. And so, to kind of make the challenges clear, let me first show you an example of a test case that our tool automatically generated that turned out to be a denial of service attack on bind, which is probably the most popular, widely used open source implementation of DNS. So this was the test case that our tool came up with. The top is showing a representation of the zone file as kind of a table. So it's got two records in it, an SOA record and a DNAME record, which I'll explain in a bit. And then below is showing the query. And it turns out that if you take a DNS name server that's implemented for bind, and you load up this zone file, and then you send that query, it causes the name server to crash. And the reason this is important is because bind is really widely used. For example, many hosting sites, DNS hosting sites use it. So if there's a DNS hosting site that uses bind, then what I can do is I can register a new domain like todd.com, and then I can go and use that hosting site to host my web page. I can install that zone file, send that query, and I crash the name server, but I crash it not just for me, but for everyone else who's using that hosting site. And then what turned out to be even worse, even though we weren't targeting it, was that this same test case also crashes DNS resolvers. And for example, many Linux distributions like Red Hat and Ubuntu use bind DNS resolvers. So that means I can crash the DNS resolver that many Linux users are depending on. And so, we, of course, confidentially disclosed this to the bind developers. They fixed it. They ended up putting out a CVE. They rated it as high severity and remotely exploitable. They called it to us a easily weaponizable denial of service attack. And indeed, it did affect all the currently maintained, at the time, versions of bind. And it affected, hosting sites like Infoblox and Red Hat and Ubuntu, Linux, and so on. So this was a big deal. But the point I want to make is that if you look at this example, there are like 4 things that have to be true in order for this crash to happen. One is that there has to be a DNAME record in your zone file. That DNAME is a kind of query rewrite, and it has to be a particular kind of rewrite. It has to rewrite from a child to a parent. That's what's happening here. It's rewriting from attack.com to com. The query has to be also asking for a DNAME record, so the query can tell can specify what kind of record we're looking for. And then the query has to at least have 2 copies or more of attack on the front of it, and it's got to end with com. And so the point is that you're very unlikely to just randomly satisfy all these 4 conditions. And for that reason, kind of standard approaches to test generation are really insufficient. Now, of course, I should caveat by saying there's a huge area of test generation, and there's a lot of interesting and exciting work. But sort of at a high level, you can think of 2 general kinds of approaches to testing software. There's kind of the fuzz testing approach where you do some kind of random exploration. And I think, there are actually fuzz testers for DNS, but they really only test for parsing errors because it's really hard to get fuzz testers to satisfy enough of the kind of semantic constraints to get you into deep behavioral errors. And then you could do something like symbolic execution where you could take like a path through the code, solve for constraints that take you down that path, but there's just way too many of these paths and too low level as well, and so it's going to be hard to get a lot of coverage that way. And so this is kind of where our formal semantics come in. So in a previous project that had nothing to do with name server implementations, it was actually about verifying zone files. We wrote a paper semantics of DNS name server lookup. And we did that so that we could prove soundness of this other tool that we wrote. And so then we had a very careful semantics of DNS lookup. And then we realized we could use that semantics to do a form of model-based testing for the implementations themselves. And so that's what we did. And so we call this approach scale. I mean, again, there are many model-based approaches to testing. I'm going to show a particular one that I think has a new collection of design decisions that I think are also relevant for other kinds of systems. So the idea is that we'll symbolically execute the formal model. So I just said the symbolic execution of the code is not going to work, but the formal model is different. It's really high level. It uses the stupidest data structures you can think of. It's made for symbolic execution. Its whole goal is just to demonstrate the different possible behaviors that a DNS name server has to handle. And so it's actually feasible to do symbolic execution for it. You'll get a bunch of tests, and then you can run those tests actually on not just one DNS implementation, but many DNS implementations to try to find bugs. One part of this that I'll come back to that I think is really critical is that we do this symbolic execution in a way that gives us coverage guarantees on the model. And I think it wouldn't have been nearly as successful if we didn't do it that way. So I'll show you a few details of how this works. So we had this formal model. It was on paper. Maybe today, this was back in 2021. Now you'd say run an LLM and have it translate it. But no, we didn't do that. We manually translated the formal semantics to a C# using this library called Zen, which is essentially makes a solver-aided programming language. So it's essentially something that if you use that library to code up the logic of your system, then you can press a button and it runs in symbolic execution mode and will generate inputs for you that take you down different paths through your code. So we can run that, and we'll get a sequence of pairs, a query in a zone file, a query in a zone file, each one taking you down different paths through our formal model. And so the way our tool works is that it does that, it generates a bunch of tests, and then it does differential testing. So it tests it on a bunch of open source DNS implementations, runs those tests on all of them. If they all get the same answer, then we say, yeah, everything's great. And if at least one of them gives a different answer, then we investigate it as a potential error. Okay, so just to remind you how symbolic execution works, I might pick the leftmost path. This is like a flowchart view of my formal model. I might pick the leftmost path through the model, collect up all the constraints that are going to take me down that path, and then I solve those constraints, and that gives me a query and a zone file that takes me down that path. I mentioned before that zone files are really highly structured. They have a lot of semantic dependencies. This solves that problem as well, because we can code up the collection of well-formadness constraints as just extra logical constraints that we have to solve here. And so we always make sure we get well-formed zone files and well-formed queries. There's still a question of, okay, how should we do this symbolic execution? Because even in our formal model, there's actually an unbounded number of possible paths through the model. And so the choice that we made was to do a kind of bounded exhaustive model exploration. So again, I think bounded exhaustiveness has been used in many domains, like Alloy used that a long time ago for exploring a model on its own, or people have done this for bound the number of concurrent interleavings of a concurrent system and then do model checking up to that bound. Here we're using it in a slightly different way. So the idea is we'll say, okay, let's bound the size of our inputs. Let's say that zone files can have no more than 4 records in them. And let's say that domain names can have size at most 4. So like foo.bar.com.baz, whatever, that's like 4. And so once we bound those things, then it turns out that there's exactly 12,673 paths through our model that are consistent with those bounds. And so what we're going to do is very simply do symbolic execution on every single one of those 12,673 paths. That yields us 12,673 tests. We're going to run them on a bunch of DNS implementations. So we ran those on 8 widely used DNS name servers and found a bunch of bugs, including at least 2 from every name server, and including that denial of service attack that I showed you before. And so the point that I'm trying to make is that this is a very pedantic form of testing, right? We're doing one test for every path through the model up to some bound, but I don't think there's any other way we would have found that denial of service attack if we hadn't covered the space completely. So yeah, everything's a program. DNS name servers, DNS zone files, we can model them all as programs. We can be then very pedantic in the way we do testing, and I don't think we would have found those kind of subtle errors if we didn't exhaustively explore that space. Okay. I just want to end with a few kind of higher level lessons that I've learned through these projects. The first one is to get real. So what I mean by that is have an important goal that if you could achieve that goal, it will actually have impact. I look back on the Batfish project, and one thing that I think really helped us was really accidental, was that when we were doing this project on network configurations, there were no benchmarks. You couldn't go find like some simple network BGP configuration benchmarks. So what did we do? We had to go and talk to the UCLA network operators and get access to the UCLA network configurations, and talk to the USC and talk to the Microsoft, and get access to their network configurations. And that meant that we had to build a real enough tool that it could actually, process these real network configurations of real organizations and find bugs in them. So by the time we even had our first paper, we were finding real bugs in real networks, which I think, if we had had some simple set of benchmarks that were already existing, we might have just used that as a target. And I think we probably never would have even started a company or done all the other things that have had an impact if it wasn't that right away we had this kind of goal that we have to at least be able to handle the UCLA network, the USC network, parts of the Microsoft network. The other thing about collaborative work is that it takes a long time. It takes a longer time than traditional work that's just in our field, because you don't even speak the same language, or if you do speak the same language, you mean different things by the same words. And so it takes a long time to understand each other and even to figure out what's a good direction. The thing I've realized over time is that it's not right until everyone's excited. Like if my networking colleagues are really excited, but I think this is just like a silly like a push button application of PL, probably I don't understand the problem well enough, because and likewise in the reverse. And so it's sort of only once everyone is really thinking that if we can achieve this, we'll do something great, that really it's right. And I would say the other thing is that at that point it really is right, and you can have faith in it, because it might still be a while before you get to the point of solving the problem. But I think if everyone feels really excited and they're coming from these different perspectives, then you can really be confident that you have something of value. Another good one is just to make friends with interesting people and curious people. So the way this whole project started, I mean, I mentioned that I started thinking about this stuff back in 2011, 2012, but actually the roots of it go back even earlier, because I was at FCRC in 2007. I don't know if anyone else was there, probably, but FCRC was like a federated ACM conference, and so there's like PLDI was there, but also Sigmetrics and ISCA and lots of other conferences. So you see people that you wouldn't normally see at conferences. And I ran into my friend Ratul, who was we were in grad school together, and he was a networking researcher, and and we were friends, but we never worked together. And we had a small conversation in the hallway there, and he asked me, "Hey, do you think you could use like program analysis to find attacks on TCP implementations?" And I was like, I don't know anything about TCP, whatever. But we started talking about that after, and that led to a collaboration. We published some papers on that. That didn't turn out to have a lot of impact outside of our papers, but what it meant was when these network reachability verification tools were coming out in 2011, 2012, we were already in a collaborative research project. We were reading these things together. We were discussing them. We were ready to take advantage of the opportunity. So definitely talk to your friends. Talk to people outside of your own local community, because those things can really, these places where different communities meet can be really powerful. And then since then, it's taken a huge number of people to have the impact that we've had. So these are the people I've co-authored papers with. There are lots of other people like open source contributors to Batfish. But the thing that I like about this is that there's many different kinds of people represented here. There's like academic PL people like me. There's academic networking researchers. There's industrial research PL people, industrial research PL networking people. And there's also like just network operators who aren't researchers, who just manage and maintain real networks. And so you kind of need all those different perspectives and expertise to be successful. So that's really what I want to say. I think that, to summarize it, programming languages are really amazingly powerful tools, maybe the most powerful tools we have for modeling and understanding complex systems. And so I've tried to demonstrate that for networks, but I think they're applicable really broadly beyond that. Maybe the thing to say today is AI, and look around at AI, and I think, can you bring the programming language lens there and have value? I think you can, and many people are doing that. But I think it even applies beyond, even beyond CS potentially, as computing becomes intertwined with like everything we do. It can apply to other kinds of sciences, medicine, things like that. This programming language lens can be really powerful. So I hope you start to think that way and find some problems to solve in that way. Okay, thank you.
All right, thank you. We have two microphones set up, one on the left and one on the right. I think that's the purpose for the question and answer session. So if you have any questions, please just come up and ask. All right, Ben, thank you. Thanks, Ben. Oh, yes, so people are coming, so I'll just host it by passing it on. All right, Mira, thanks.
Hi, Todd. Thank you very much for the very inspiring talk. Exactly. These 3 points are very good take-home messages. Find programs, be pedantic, make guarantees. I have a question regarding the work on Lightyear. How involved are the local invariants that you have to express? And more specifically, are there dependencies between the invariants or specifications for the individual nodes that you might want to express?
Is this on? Yeah, okay. Great. So, yeah, I think for Lightyear, the hardest part is actually figuring out what those local invariants are, because the network operators don't have them written down anywhere. They're kind of in someone's head. And so what it tends to be is kind of an iterative process. Like they'll tell us, oh, what I'm trying to ensure is that, I'm using this particular tag to ensure X. And so then we make a guess at what the local invariant is. We run it. We get a counterexample. And then we go to them and we say, hey, we got this counterexample. And they say, oh, no, that's OK, because Brazil, we have a different agreement with them, and so we treat that a little differently. And so for Brazil, we don't have to worry about that. And so then we have to refine our invariant. And so these things can get complicated. But you can always boil them down to local properties, because, I mean, inherently, these things are configured locally. So each sort of like you can always do that. I think your question is like, in practice, is it going to be more convenient sometimes to express them as relations across different nodes, and we have not explored that yet, but it might be something to consider. We haven't needed that for the simpler kind of properties, but maybe as things get more complex, yeah.
If I thought about them like a type system or typing specifications, my question was like how expressive this specification language has to be, and do I need like something equivalent to dependent types?
I see. Yeah. I mean, right now, the language is sort of like what you can boil down to an SMT query. And so, what you can express as a logical constraint on a route. So the predicates are of the form, given a route R, here's a property P that must hold of that route R. And that property P is just something that can be expressed as an SMT constraint. So that's like our limitation right now.
Well, can I go next? Because I also wanted to ask about types.
Types?
You're the boss. All right, great. Let me ask about types. So you found some very exciting critical bugs up to bound 4. What do we do to catch the bugs, the rest of the bugs, bound 5 and beyond? Do we need bigger machines? Do we need a type system? What do you recommend?
Yeah, that's a good question. Well, I think, you know, I didn't say it explicitly, but the hope is that there's something like a small model or small scope hypothesis, meaning that, you know, like of course in the real world these DNS configurations have thousands of lines in them, but if you look at any particular query, it's only going to touch a small number of those records. It's not going to touch all of them. And so, you know, I mean, of course there could be bugs that go beyond 4, but the hope is that 4 is actually still capturing a lot of complex behaviors. Now the question is, okay, how do you go beyond that? So I mean, I think there are two things that would be interesting. One is, of course, you can just run more, you know, get at cloud scale and start running these things at 5 and 6 and 7 and give yourself more confidence as you find fewer bugs. I think the other thing would be if you can actually prove that a certain class of errors, that, you know, there might be cases where for certain classes of errors at least you can prove that if there's a bug you'll find it in a small model. So I think that would be interesting. The other thing that I think is interesting, which is maybe related, is we're not catching resource bugs, and those are an important class of bugs, and those do only occur when there's a big scale. Like if you overflow a cache or overflow a buffer or something like that, that's not going to happen if your records have size 4. It's only going to happen when you have, you know, huge numbers. So we're not catching those kinds of performance bugs, and that would be really interesting to figure out how to do that. Yeah.
Great work. Is it on now? Great work. I was really gratified to see that this sort of brute. No, it says on it. All right, thank you, Todd. It was great work. I was really gratified to see that the sort of brute force enumerative path checking, that was so effective. Do you feel that model checking techniques that are really working on scaling up, do you think, obviously it's a very fruitful direction, but do you think that applying even brute force techniques to a domain like you found, do you think that is a more productive direction for model checking?
For model checking? I don't know. I think it really depends on the domain and the area, right? I think it also even depends on what kinds of properties you're looking for. So I think it worked in this setting because we're looking for behavioral errors, and even up to size 4, you can exercise many interesting behaviors because you can rewrite things in interesting ways. You can have queries redirect to other queries. You know, size 4, you already have a lot of weird complexity. You know, I think, like I said, that wouldn't have worked if we were looking for performance bugs. Like we wouldn't find a resource constraint limitation or something like that. So I think it's not like a one size fits all. I think it's more about what it worked for this class of programs and this class of properties. But you know, I think you'd have to think about that for other kinds of programs and properties. Yeah.
Well, thanks for your talk. I'm Youwei from Shanghai Jiao Tong University. Oh, sorry. I work on the formal verification of zero-knowledge virtual machines, which I find is similar to your. And I have 3 questions for you. The first one is, you said you use real-world forward tables to formalize your models, and I want to know, how do you formalize these tables from different countries, companies and the universities? Do they share a similar model or what? And the second question is that what will happen if they update their protocols? For example, there are many requests for comments, new requests for comments every day, and if they change the protocol, will your formal model still stand? And the third question is, you said you use some symbolic execution tools to help you get these corner cases, but do your tool have some soundness guaranteeing or what? For example, if you can formalize your tool in proof assistance like Coq, you can have some sort of soundness guaranteeing. Otherwise, you may not, if your tool has some bugs, you may not find all the corner cases or what. Yeah, that's all my questions. Thank you.
Okay, thanks. I think I got all those. Let me see if I can answer them. So I think about the first question. Yeah, I didn't mention this very much, but there are several different configuration languages. Like the different vendors, like Juniper has their own language, Cisco has its own language, Arista. And even within a single vendor like Cisco, there are different flavors of the same configuration language. So we have to actually parse all of those. We parse them into, our data model is vendor independent, so we parse them all into a common data representation so that even if you have a network that uses different kinds, which is actually very common, it's very common to have different kinds of, like Juniper and Cisco in the same network, then we can reason about them in a unified way. You asked about what if they change the RFCs or add new features and things like that. So I should say, like, you know, DNS is huge. There's like, and we're not handling all possible things in DNS right now. We're handling the most common things. And so, for example, like DNSSEC is like a security extension to DNS, and there are certain record types that are specific to DNSSEC, and we're not handling that. So we ignore those records. So we're not generating test cases with those records. If people extend the protocol, that's okay, as long as it's backward compatible, as long as the stuff we are handling has the same semantics, then our tests will still be valuable. We could update our model, our formal model, to handle new record types as they come out, and we have done that actually a little bit over time. But the old stuff shouldn't break unless they change the semantics of the old stuff, which would be crazy to do at this point because you've got decades of you know, they're not going to do that. So yeah, I think the last question was about soundness. No, we don't have any. You know, so yeah, you could.
But you see, people don't use formal methods because they don't have the expertise in these fields. So maybe they invent new protocols in a speed that you can't come up with.
Sorry, I didn't get the.
Maybe they update the protocol every day, and you can't form these protocols in a day.
So the protocol update, I'm not sure if I got your question, but the protocol update process is not overnight. It's like there's a whole there's a community that has to review these considerations, and there's a internet IETF, the Internet Engineering Task Force, that has to review these things, and these are not done lightly. So these are things that have a process to them. So yeah.
Oh, thank you.
Hi, Todd. Hello. Audible? All right? No, yeah. We start the break at 10, which is in 3 minutes. You want one more question? Oh.
Yeah, the last question is... Yeah.
Let's take this discussion offline, and Krishna can ask the last question, okay?
Oh, okay.
Yeah. That's right. So after Krishna's question...
Okay.
Thank you, Todd, for a very inspiring talk. Had a question. In your protocols, have you looked at properties which involve timeout? And did you model them using some timed automata, or what's your experience with that?
Okay, yeah. So no, there are timing issues in BGP. Like BGP may not, and depending on the order of operations and the timing of things, it may not even converge, for example. Yeah. And so we have to deal with that in our simulation, but we're not actually trying to check properties of timing. We're just trying to get our hands on the quiescent, the final state of the network, the forwarding tables that are produced at the end. And so we have to deal with timing in so much as we have to deal with convergence issues, and we have to play some tricks. Like there are cases that might converge, not converge in theory, but do converge in practice, and so we have to figure out how to handle those cases. But we're not actually reasoning about time directly.
Take issues. We had this thing of, I think in 2005, we had tried to prove the property stack. We found it useful to use an OOPSLA of tool to model the behavior and properties of TCP stack. So.
Okay, it's hard to hear now, so I think let's take it offline, but I'll be happy to talk more about it.